So let's talk about pressure and what pressure is in terms of gases in science. And I'm sure you all have your own definitions of pressure and stress. So pressure is predicted by the kinetic molecular theory, and it's the result of those collisions of the gas particles with the surfaces around them. So you can imagine, if we're throwing baseballs at the whiteboard, every time you throw a baseball at the whiteboard, it's going to exert pressure on the board, right? So there's pressure from particles hitting things. Now, the gas particles are very, very tiny. They're on the size of atoms and molecules, and we've learned that those are, mind-bogglingly small. But they're moving fairly quickly, and the thing is, they're hitting the surface a lot, okay? So, you could get punched by a boxer once, and that's going to hurt a lot. Or you could have the 4-year-old punching you in the stomach, and at first you're like, yeah. But when it goes on and on and on, it adds up after a while. Not that I ever let him do that, but I've seen him do it to other people who were willing to put up with it. They're beating on you with their little fists, right? Something small that happens a lot can be just as significant as something large that happens infrequently. So we have these gas particles hitting things, and they're causing pressure. So this pressure of gases is important in our everyday lives. Because of that, we can drink from straws. I'll drink from my straw. Could we live without that? Sure we could. We could just drink out of the cup regular. We can inflate basketballs, footballs, soccer balls, because of the pressure. The pressure of the gas inside the ball holds it open so it doesn't just collapse on itself. We can move air in and out of our lungs because of gas pressure. Now that one's pretty important. Our weather is dependent on gas pressure. So we get variations in pressure which cause wind and different types of weather. And one way they predict the weather is by looking at how the atmospheric pressure is changing. It doesn't change a lot, but it does change a little bit. So on the news, when they say the barometric pressure is such and such, that's the pressure of the atmosphere in that location that day. And they can say it's rising, it's falling, and that alerts them that, okay, this certain sort of weather system is coming. So pressure is important. So here, if we look at these two, I think it's kind of friendly. These look like mason jars, don't they? So here we have two jars, same size, so they have the same volume. This one has fewer particles than this one. So the particles are at the same temperature, they're all moving at the same speed, and they're the same type of particles, so the same mass. So they have the same kinetic energy. They're hitting the walls with the same amount of force. But in this one, because there's fewer particles, there are fewer collisions in a given amount of time. This one has more collisions. Or we can think of fewer collisions in the same surface area. So we have an equation for pressure. So, not that. Pressure is force per unit area. So it's the force per unit area. So if you have the same force, but it's spread out over a larger area, then the pressure is less. If the area is smaller, the pressure is more. So say you had a, 80-pound little girl sit on your stomach. Okay, so you're like, yeah, there's pressure there. But, just sitting on you or laying on you, it's not unbearable at all. But if she put on high heels and stood on her heels, little tiny stiletto heels, so what little girl should be wearing those, but if she did that on your stomach, That would hurt. Old, we used to have linoleum. People don't actually have linoleum anymore. But a regular-sized woman wearing stiletto heels can poke holes in linoleum because her whole body weight, say even just 100 pounds, on a quarter-inch square, it's a significant amount of pressure, and it can punch holes in things. So there's a relationship between the amount of force and the area. So if we look at these two jars, they're the same volume, they're the same size. The inside of them should have the same surface area. Does that make sense? They're the same jar. But in this one, we have fewer particles, and this one we have more. So there's going to be more force over the same amount of area than in this jar. So this jar has a higher pressure, because the pressure is dependent on the number of particles and on the area. Okay? So the pressure depends on several factors. Number of particles is one of them. So when you go up into the mountains or you get in an airplane, you go up in elevation, the atmospheric pressure decreases. Here's an illustration of your ear. So here's your inner ear, and there's your ear canal, and you've got this eardrum in here, and that's what allows you to hear the vibrations in there. So on one side of your eardrum, it's open to the atmosphere. The other side of the eardrum goes through the eustachian tube in your neck and into your esophagus somewhere. I never took anatomy. But eustachian tubes allow the pressure inside your ear to equalize with outside. And so that's why you go up into the mountains and your ears start to feel funny, because you get this pressure imbalance, and that causes your eardrum to bulge, which is not comfortable. So what do you do to fix that?
Chew gum.
You chew gum, or you yawn, or you swallow something. You move your jaw, and that helps your eustachian tube to open up and allow the pressure to equalize. Tommy had a couple of earaches this weekend because he's like super congested. He's like snot head, and he like sniffs, and you're like, oh my goodness. Anyway, so his ears hurt. Why do his ears hurt? Well, there's all this swelling and congestion. His eustachian tubes are all clamped up, and pressure builds up inside your ear, and it can't get out, and so it's really uncomfortable. So you get this pressure imbalance between the inside and the outside of your eardrum. Pressure units. So pressure is a quantity, and so we have to have units to measure it in. The simplest one is an atmosphere. The abbreviation is ATM, which is not an automatic teller machine. And that's defined as the average pressure at sea level. So, we just talked about weather and how atmospheric pressure varies, but they've apparently determined, okay, whatever, this is average pressure at sea level. And then there are other units, and we should just be aware of them. The SI unit of pressure is called a Pascal. That was named after Pascal. It's defined as 1 Newton per meter squared. A Newton is a unit of force, and a square meter is a unit of area. A lot of the SI units are based on very, very simple units, and they're great if you're doing derivations and weird calculations and stuff, but they're not really all that useful. So we don't use newtons per square meter in chemistry much. But we talk about it because you should know that it exists, I guess. But a Pascal is much smaller than an atmosphere. We use atmospheres a lot. So here's the relationship. An atmosphere is 101,325 pascals. So an atmosphere is much bigger than a Pascal, and you do not need to memorize that number. Another unit of pressure is millimeter of mercury. And that sounds like a very weird unit. A length of an element, how is that a unit of pressure? Well, this came about from work done by Torricelli, and he invented the first barometer, and it was something like this. So there's a dish of mercury. Mercury is a metal, but it's a liquid at room temperature. It's really fun to play with, and it's really just awesome, and it's also really toxic, so we don't get to play with it. But what he did is he took a long tube, he filled it completely with mercury, and then inverted it into a dish of mercury. And the mercury started to run out and then stopped. And what we have up here is a vacuum. And this column of mercury, just like the soda in the straw, is being supported by the atmospheric pressure pushing down. Now the difference between the mercury and the soda is the mercury is much more dense. Soda is going to have a density similar to water, which is about 1 gram per milliliter, and mercury is 13.6 grams per milliliter, so almost 14 times more dense. So the weight of it is going to have a lot more force pushing down, and so atmospheric pressure being the same cannot support the same height of a column of mercury. It will support a column of mercury that is 760 millimeters tall, or 29.92 inches tall. And that's just, if you convert millimeters to inches, that's the number you get. 760 millimeters is the same as 29.92 inches. So the sorts of things he did is he did this barometer, and then he took it up a hill, up a mountain. And as he went up the mountain, the height of the column of mercury got shorter. Interesting. Then he walked it back down the mountain, and the height of the column of mercury went up again. I was like, oh, wow, okay, so what's causing that, right? Because this is back a long, long time ago. I think on the next slide we have the actual dates. It's the atmospheric pressure. You can measure atmospheric pressure in this way. Mercury works a lot better because if we did this with water, you'd have to have a tube of water that's 34 feet tall. Okay, that's not going to fit in the room, right? It's just not real practical. 760 millimeters, though, 29 inches, that's less than a yard. So that's a much more reasonable thing. And when we go over to lab today, we actually have a mercury barometer on the wall. You probably didn't notice it, but we'll look at it. It's kind of cool. So average atmospheric pressure will push that column of mercury up to 760 millimeters. So that's where the unit millimeters of mercury. A pressure that will support a column of this many millimeters of mercury. So it is a length of an element. It's kind of weird. So there's some other units. This is a table from your book. I do want to point out that there is a mistake in the book. So look at this guy. In your textbook, it says 29.92 atmospheres. It's supposed to be inches of mercury. Inches is also a length, so you can measure the height of the column. So this table is nice. The ones I want you to memorize are these guys right here. So we talked about the Pascal, we talked about the atmosphere, millimeters of mercury. A torr, okay, so 760 torr is the same as 760 millimeters of mercury. So they recognize that, millimeters of mercury that's kind of a weird pressure unit. Let's honor Torricelli and make a unit of pressure that honors him. And so they call it a torr. And I'm not exactly sure why we use both of them. Maybe just to confuse students. A torr is exactly the same as 1 millimeter of mercury. And the atmosphere is defined as 760 torr, or 760 millimeters of mercury. So on this table where it says exact, that means that those are exact conversions, and you don't think about significant figures when you use those. The way this table works is that all of these quantities here are equal to each other. So 101,325 pascals is equal to 1 atmosphere, which is equal to 760 millimeters of mercury, which is equal to 760 torr, which equals 14.7 pounds per square inch. A pound is a unit of force, or PSI, and that is equal to 29.92 inches of mercury, not atmospheres. But you should remember these guys over here. An atmosphere is 760 millimeters of mercury or torr. So that's one number you have to remember. It'll save you a lot of time. So let's do a couple of examples. Here's dimensional analysis. Come back to haunt us again. I'm going to show you how to use this table. So convert 1.25 atmospheres to torr. The nice thing about the way that table is set up is all of these are going to be one-step conversions. And your book, I don't know why, in their example, they make it into a two-step conversion. It's just not necessary. So we want to go atmospheres to torr. So we'll put torr on top and atmospheres on the bottom. Then we look at the table. And we see 1 atmosphere equals 760 torr. All of these are equal. Okay, so the pressure unit conversion factors are set up differently than other conversion factors are. So they're all equal. So we just look at the table and we see that 760 torr is the same as 1 atmosphere. I forgot to get out my calculator. I like this new iOS 7 on the phone because you can get at your calculator without actually unlocking your phone. Okay, so 1.25 times 760, I didn't leave any space to write the answer, 950 torr. So atmospheres cancel out. Now, how many significant figures should that number have? 3. 1 atmosphere equals 760 torr is exact. We started out with 3 significant figures. As I've written that answer, is that a good way to write it? No, because it's ambiguous. So you could put a decimal point there, and that would technically make it 3, or what best is 9.50 times 10 to the 2 torr. And we're just going to keep practicing significant figures all semester. That'll be great. Okay, let's do this one. 350, where does that come from? 300.15 inches of mercury.
254 millimeters in an inch.
30.15 inches of mercury. And here we've got millimeters of mercury and inches of mercury. Put the units in. And so what's the relationship between millimeters of mercury and inches of mercury?
254 millimeters per inch. Because a centimeter is 2.54.
Let's look at the table, it's easier. Well, you could do it that way. You can do it that way. But if we just look at the table, 760 millimeters per 29.92 inches.
Oh, okay.
Okay? The other way is to say, well, 1 centimeter, no, 1 inch. 1 inch is 2.54 centimeters, which is 25.4 millimeters. And so you can convert it that way too, and you'll come up with the same answer. So we get 30.15 times 760 divided by 29.92. And that should have four sig figs, so 765.8 millimeters of mercury. And if you do it with the other one by multiplying by 25.4, you get the same answer. Okay, so this shouldn't be too hard for you guys. Let's do one more. 173 inches of mercury, 2 pounds per square inch. But the table's not on here. So 173 inches of mercury. Pounds per square inch is PSI. Down here, inches of mercury. Does anybody have the table in front of them? No? Well, if we were looking at the table, in front of inches of mercury, it says 29.92. And in front of PSI, 14.7. Those numbers, if you needed them on an exam, I would give them to you. I won't give you the 760 though. So times 14.7 divided by 29.92 equals, we should have 3 sig figs. It says 84.996, and so we're going to have to round that up, right? 85.0 PSI. And a common mistake students make when they round up is that they don't put the 0 in there. You rounded up correctly, but then you left out the third significant figure. Any questions?